the focus of this lesson is on writing the factorization over the complex numbers and also over the real numbers, given the specific information that is listed here. And so in this example, we're told that the degree is 4, the leading coefficient is 2, and the zeros are 5 minus I and 3I. So based off that, if I'm trying to come up with a factorization for my polynomial, I can call it p of x or any name I want to give it. I know that the leading coefficient is 2, so that means a is 2. So there's a multiplier of a that exists beyond all the factors that are also present in the factorization. It says that the degree is 4, so what that means is there's at most 4 zeros, and we're actually given 2 of the zeros. So the zeros that we're given are 5 minus I and 3I. Well, we know that imaginary zeros occur in pairs. In fact, their conjugate also has to be a 0 if they exist. So the conjugate of 5 minus I is going to have the same real part but the opposite imaginary part. So this will be 5 plus I. And then the same thing for 3I, the same real part, which is just 0, and the opposite imaginary part, which is negative 3. And so this gives us negative 3I. And so we can see at the end of the day that we do have 4 zeros. And so if we have 4 zeros, that means that we have 4 factors. And the way you get factors is you just take x minus your 0. So I'm going to go ahead and just list x minus a parenthesis set 4 times, and then what I'm going to put in that parenthesis set is just the zeros that I had, and that's how I come up with all my factors. So the zeros are 5 minus I, 5 plus I, 3I, and then negative 3I. And then I do need to simplify that information, but when I do, I'm gonna simplify it up here in my factorization. It becomes x minus 5 plus I, so don't forget to distribute that minus sign. X minus 5 minus I, x minus 3I, and x plus 3I. And so at the end of the day, I want to compare this back to the information that I was given, and I can see that it does have a leading coefficient of 2. It takes into account the fact that the degree is 4, because you can see that there's 4 factors here, and it also takes into account the zeros that we were given, along with the conjugates zeros that we use to get our other 2 factors. And so this is the factorization over the complex numbers. Now we're going to go ahead and focus on the factorization over the real numbers, and in doing that we're going to still have the same leading coefficient of 2, so we can go ahead and list that down. But what we're going to do differently is we're going to end up multiplying together these conjugate factors and making irreducible quadratic factors instead. So instead of having 4 linear factors like we do in factoring over the complex numbers, we'll end up having 2 pairs of irreducible quadratic factors. And so I'm going to go ahead and take care of the x minus 3I times x plus 3I piece first, just because the multiplication of that is probably easier than the other pair that we would do. And all we're going to do is use foiling. And you'll see that there's a pattern in the foiling as you go along. First times first comes from the fact that it's x times x. Outside comes from the fact that it's 3I times x. Inside is from negative 3I times x. And then last is from 3I times negative 3I, and I'm going to put the negative one here just so the negative's in front, and so it's negative 3I times 3I. And so then you go ahead and you simplify each of these, and in doing so you see that you get x to the second, 3ix, negative 3ix, and then negative 9 I squared. And so notice when you have I squared is -1. So what that does is instead of writing I squared, it's going to change your sign and that I squared piece disappears. So it's -9 times a -1, which ends up being a +9. So just be aware of that. And then notice that the 3ix and the -3ix are opposite, so they're going to add out to 0. So all of this together just goes to x squared plus 9 if you combine them. So that's one of your irreducible quadratics. So then you need to repeat that process, but you're going to do it for the second pair. So when we take the second pair, notice this is a little more complicated looking as far as our factors. In fact, what I'm going to do is I'm going to group so that the imaginary piece is by itself. So I'm going to group this x minus 5 together and leave the imaginary piece by itself. And then I'm going to do the same thing for that second factor. And this is how I'll always do it. And then when I do my foiling, I'm going to actually kind of have foiling within foiling, and I'll show you what I mean. But when I do my first times my first, I'm going to take the group x minus 5 times the group x minus 5. So that's my first times my first. So I was very intentional on how I grouped to get that. And then outside, I'm going to have -I times x minus 5. And then inside, I'm going to have +I times x minus 5. And then last, I'm going to have -I times +I. But then if we simplify, this first piece, x minus 5 times x minus 5, is just foiling, which will give us x squared minus 5x minus 5x, which is minus 10x, plus 25. And then we could simplify this second and this third piece, but you can see that they're identical other than the outside piece had a negative and the inside piece has a positive I. And so at the end of the day, those are opposites, and that will always be the case based off of the way I did my grouping. And so you don't even have to worry about doing that multiplication and distributing. And then -I times I is -I squared. But again, remember I squared is -1, so this is -1, which just ends up being a +1. So I'm going to add that to my FOIL piece to get my whole factor. And so my irreducible quadratic is x squared minus 10x plus 26. And so at the end of the day, my factorization is similar, but it's, like I said, irreducible quadratic. So this completes the factorization over the real numbers.